Hello and welcome. In this lesson, we'll explore families of polynomial functions. A family of polynomial functions, as the name says, it is made of polynomial functions that can create a family. When I think of the definition of the word family in everyday life, I would say that a family is made of a group of items or people that share important features. Another way of describing it would be a family is a group of items or people that have common roots. And I'm going to use the word roots in this case because it's perfectly transferable to describing families of polynomial functions. When we say roots, we can also say x-intercepts because that's another word for roots. And we use it when we're graphing a polynomial function or any function, or the zeros. And that's what we call the roots when we are solving a polynomial equation. Now, I want you to pause for a second and think. If polynomial functions that have the same roots make a family, what would they look like? Now, remember that polynomial functions differ from one another based on their degree. So, for example, first degree functions will have common features, second degree functions common features, and so on and so forth. And for a group of polynomial functions to have the same roots, it means that this group must be represented by polynomial functions of the same degree. And this is the reason why we are going to start by exploring different degree polynomial functions, and we're starting with the simplest and more fun one, the linear functions. We are going to analyze linear functions from the first differences perspective because we are about to discover some cool patterns. Now, when it comes to linear functions, remember we've done them in grade 9 as well, so nothing surprising in here. It will get more exciting as we move along though. So as examples, I took in here y equals 3x minus 2, y equals negative x plus 3, and what we're going to do is find the first differences. Now, just a few little things before we get started. First differences are represented by this little triangle in here. And you see that we have subscribed the letter, subscripted the number 1 here. Now this letter is actually the letter D in Greek, and it stands or it's used as a symbol for the word difference in mathematics. You probably knew this already. Okay. Now, when we find first differences, it's very important that we first examine the values of x. It's important that the values of x are equidistant from each other, which means that the values of x must increase or decrease by the same amount. So in this case, what we have is the values of x going up by 1. So they're increasing by 1 unit, which means that we are in the perfect territory here to analyze the first differences. So I started off by finding the values of y. I did that ahead of time to save some time. This is how I find the first differences. I start off with a y value and subtract the previous y value. Negative 5 minus negative 8. And that's the case in finding any differences in any type of relation. So we always subtract the previous number from a y value. So negative 5 minus negative 8 is positive 3. The same thing applies in the next differences. Negative 2 minus negative 5 is also 3. 1 minus negative 2, that is 3. And 4 minus 1 equals 3. So as you notice in here, we have same first difference in every set of y values that we work with. Now we're going to look into the next relation. So we have 4 minus 5, that's negative 1. 3 minus 4, negative 1. 2 minus 3, negative 1. 1 minus 2, negative 1. Again, we notice that the first differences are constant, so are the same in this linear relation. Now, that leads us to think that, oh, so in linear relations, the first differences are constant. And you probably notice something else. You see that the first differences here in the first relation are all 3. And you probably notice that number 3 actually is part of the equation as well, and it's in the spot of the slope in here. So another thing I can think of is not only first differences are constant, but the first differences will represent the slope of the equation. And the same thing applies in here. The first differences represent the slope, but then we still think maybe this is a coincidence. So why not prove it together? So in order to prove that the first differences will represent the slope of the equation, what we're going to do is look into the equation of the line in the form y equals mx plus b, which is a more general form. It's not a specific equation. So it is very important, again, especially when we are trying to prove that the first differences will represent the slope, that not only the x values are changed by the same amount, but they must be changed by 1 unit exactly. So it can be an increase or decrease, that doesn't really matter. So in this case, all the x values are increased by 1. Now let's look into the y values. So the y values are found by substituting x into the equation. So if x equals -2, then the y value will be -2 times m plus b. If x equals -1, the y value would be -1 times m plus b. If x equals 0, it will be 0m plus b, or simply b. If x equals 1, it will be 1m plus b. And when x equals 2, 2m plus b. So let's start with the differences. I'm going to do the first one, show all the steps. So let me focus everything. And here we go. So we have -m plus b, subtract -2m plus b. So that would be -m plus b plus 2m minus b. Notice how the b's will simplify, and -m plus 2m would equal m. So there we go. The first difference was m. And we hope and expect that the same thing will happen in every difference, in every delta 1. So here we go. We have b, take away -1m plus b. So that again would be b plus m minus b, or simply m. So we got the same difference. So we are sort of convinced now that we're going to get the same first difference in every step. So m plus b, take away b. That is easier, m. And the last set would be 2m plus b minus 1m plus b. So that would be 2m plus b minus m minus b, or again, m. So now we are super convinced that the first differences in a linear relationship, providing that the x values are differing by 1 unit, it can be plus or minus 1, doesn't matter, will represent the slope of the equation. And this would be our number 1 conclusion. So delta 1 would equal the slope, providing that x values differ by 1, unit. And another thing that we want to actually look into is the Y-intercept. So what I'm going to do is highlight the Y-intercept in every equation. And I want us to look at the table values and check and see where we find this value on the table. So -2 is present in this table of values right here in this spot. positive 3 is right here, and b is right here. And if you look into the relation described in the table of values, when y value is negative 2, or at the y-intercept, x equals 0, which makes sense because at the y-intercept, x equals 0. So 3 happens when x equals 0. B happens when x equals 0. So we'll also say that the y-intercept will be found at x equals 0. So at x equals 0, y equals b. And this will help us find the equation of a linear relation when the relation is given in a table of values. So let's try it in this example. So on this table, we have a relation described by a table of values. We don't know the equation. So let's go ahead and find it. So I'm going to start off by checking the x values. The x values are all differing by 1 unit, which means that if I find the first differences, then the first differences should represent the slope. So let's go ahead and find the differences. Remember that we go backwards. 8 minus 14, negative 6. 2 minus 8, negative 6. Negative 4 minus 2, negative 6. Negative 10 minus negative 4, it's negative 6. And negative 16 minus negative 10 is negative 6. So we're going to say delta 1 equals negative 6. Therefore, the slope will be negative 6. For the y-intercept, we're going to say that will happen at x equals 0. At x equals 0, if you look at the chart, the y value is 2, which tells us that b equals positive 2. So the equation will be in the form y equals mx plus b. And in our case, with the slope of negative 6 and y-intercept of 2 will be negative 6x plus 2. Voila, this is the answer. Now we're going to move on to quadratic functions. So we're doing something similar in quadratic functions. Remember, quadratic function in standard form is given as y equals ax squared plus bx plus c. We're looking into various quadratic functions, specific equations, and we're going to find the differences. Remember, delta 1 stands for first differences, delta 2 for the second differences. Again, we have to check and see if the x values are changed by the same amount. And in this lesson, actually, they are all changed by the same amount. There are no tricks to it because we are simply exploring the functions, right? But when you are practicing homework questions or other questions, we always have to remind ourselves of it. So here we go again. We have 2 minus 5, negative 3. 1 minus 2, negative 1. 2 minus 1, positive 1. 5 minus 2, positive 3. As you notice here, first differences are not constant. And that will make us think that this relation is not linear. We already know it, right? Now, we're going to move on to finding the second differences. Second differences are found in the same way. We call them second differences because they are the differences of the first differences, right? So we are finding the differences for the second time. So we have negative 1 minus negative 3, that's positive 2. 1 minus negative 1, positive 2. 3 minus 1, positive 2. Moving on to the next relation. Again, I found the y values ahead of time. So negative 1 minus 5, negative 6. Negative 3 minus negative 1, negative 2. Negative 1 minus negative 3, positive 2. 5 minus negative 1 is 6. Let's move on to the second differences. So we have negative 2 minus negative 6, that's a 4. 2 minus negative 2 is 4, and 6 minus 2 is also 4. So second differences are constant. It's a quadratic relation. One last time, we have 6 minus 16, negative 10, 2 minus 6, negative 4, 4 minus 2, positive 2, 12 minus 4, positive 8. First differences, as expected, are not constant. So we're going to continue with the second differences. Negative 4 minus negative 10, 6. 2 minus negative 4 is also 6. 8 minus 2 is 6. So second differences are constant, typical for quadratic or second degree polynomial functions. Now, together we want to recognize or understand if there or explore whether there is any pattern that can help us using the differences in order to find the equation of a quadratic relation when we are given just a table of values. So in order to consolidate the patterns, what we're going to do is look into the equation of the quadratic relation in a more general form. So y equals ax squared plus bx plus c. So I substituted the values of x ahead of time. And what we have in here is at x equals negative 2, a times negative 2 squared is 4a, plus b times negative 2 is negative 2b, and then plus c. The same thing was done for the rest of the y values. So we're going to get started with the first differences. So we have a minus b plus c, take away 4a minus 2b plus c. So that would equal a minus 4a, negative 3a, negative b plus 2b, that would be b, and c minus c is 0. So let's move on to the next set in here. So I'm going to highlight them because it's getting a bit crowded. Let me make this bigger. So the next set of y values, c minus a minus b plus c, which would equal c minus a, negative a, I'm going to list them in order as well, plus b, and c minus c equals 0. So next we have a plus b plus c, take away c, that's easier, a plus b. Again, I'm going to highlight the first differences. And last but not least, we have 4a plus 2b plus c, take away a plus b plus c. So that would be 3a, 2b minus 1b is 1b, and c minus c equals 0. So we'll continue now with the second differences. So here we go. We're going to start off with negative a plus b, take away negative 3a plus b. So we have negative a plus b plus 3a minus b, or even better, let me bring this higher, 2a b minus b is 0. Now we're going to do the next set of y values, or differences in y values. And you know what, I'm going to do this actually, because we can see them a bit better this way. So we have a plus b minus negative a plus b. So this would be a plus b plus a minus b. Surprise, surprise. The answer is 2a. Last, we have 3a plus b minus a plus b. So that would be 3a minus a, 2a. b minus b, 0. So here we go. Let's proudly highlight them. And notice how the second differences, not only they're constant, but the second differences equal to A. So we'll be drawing some conclusions together. So conclusion number 1, delta 2 equals 2A, which means double the coefficient, the leading coefficient. And there are other things that we need to actually get from this investigation. So the value of C. The value of C, as you can see in here, happens at x equals 0. So C is the value of y at x equals 0. And we can also actually look at other patterns in here where we can describe the value of b. And this is not necessary as a matter of fact because the value of b can be found algebraically. So let's take an example where we are going to use all these conclusions to find the equation of a quadratic relation when the relation is given by the table of values, by a table of values. Here we go. So we are given a relation. Here are the x values. They're all differing by 1 unit. And here are the y values. We don't know the equation that describes this relation. We just know the values of x and y. So we're going to find the equation, and we'll start off by finding the first differences. We need to first identify what kind of relation this is. 0 minus 3 is negative 3. 1 minus 0 is positive 1. 6 minus 1 is positive 5. 15 minus 6 is 9. 28 minus 15 is 13. So obviously is nonlinear because delta 1 values are different. So moving on to second differences. So 1 minus negative 3, 4. 5 minus 1, 4. 9 minus 5, 4. 13 minus 9, also 4. This is funny. So second differences are constant. N equal to 4. So therefore, we're going to say that this is quadratic or second degree polynomial. So since this is a quadratic relation, that means that the equation can be in the form y equals ax squared plus bx plus c. So now we are thinking, what do we need to actually write the exact equation of this relation? So we're going to need to know what the value of A is, what the value of B is, and what the value of C is. So we know that delta 2 equals double A. In our case, delta 2 was 4, which tells us that the value of A must be 2. Another important coefficient that we can readily find on the table of values is the value of C. So the value of C happens at x equals 0. And we're going to say that C equals y at x equals 0. And in our case, C must equal 1. So we're going to say that we have 2 of the coefficients. We have the coefficients A and C. We can substitute them into the equation. So y equals 2x squared, we don't know b yet, plus bx, and then plus 1. Since we're missing only one coefficient, remember we have this big table of values with lots of sets of ordered pairs, right, that can satisfy the equation. We can pick any ordered pair, substitute it into the equation to find the value of b. Now, I would pick any of the ordered pairs, but I wouldn't pick the intercept here or the value of c because it's already been used in the equation. But nice numbers to work with here would be 1 and 6, both positive and not so big. So if we pick the point with coordinates 1 and 6, it means that when x equals 1, y equals 6. So we'll substitute y by 6 and x by 1. So we have 6 equals 2 times 1 squared plus b times 1 plus 1. And as you see, now we have only b as unknown in this equation. So 6 equals 2 plus b plus 1. I'm going very slow here. So it seems that b equals 3, everyone. So here we go. We have the values of b, a, and c, which means that we're ready to state the equation of this linear quadratic relation. So we'll say that that would be 2x squared plus 3x plus 1. And voila, this is the answer. Now we have another example here you can try on your own. We're moving on to the last group of polynomial functions, the cubic functions. The procedure is the same. Remember that a cubic function in standard form would be ax squared plus ax cubed plus bx squared plus cx plus d. First, we're looking into two cubic equations, and we're going to use the table of values to find the differences. Again, the procedure is the same. Check with the x values. They must be equidistant. And we'll start by finding delta 1. Negative 3 minus negative 15, that's positive 12. 1 minus negative 3, that's positive 4. 3 minus 1 is 2. 9 minus 3 is 6. And 25 minus 9 is 16. As you notice here, delta 1 first differences are not constant, so it's non-linear. Let's move on to finding delta 2. The second difference is 4 minus 12 is negative 8. 2 minus 4 is negative 2. 6 minus 2 is 4. 16 minus 6 is 10. So as you notice, the second differences are not constant, which means it's non-quadratic. So not first degree, not second degree. Let's move on to the third differences, which basically are the differences of the second differences. So negative 2 minus negative 8 is positive 6. 4 minus negative 2, 6. And 10 minus 4 is 6. So what I notice in here is that delta 3 values are all constant for this particular relation. I expect the same thing to happen with the next equation, but I'll try one more just to be sure. Now, here we go again. We have y equals 2x cubed minus 3x plus 4, a cubic equation, and I found the x values, the y values based on the given x values. And let's start off with the first differences. So we have 5 minus negative 6, 11. 4 minus 5, negative 1. 3 minus 4, negative 1. 14 minus 3, that's 11. And 49 minus 14 is 35. First differences are not the same, so obviously is non-linear. Moving on to second differences, we have negative 1 minus 11, negative 12. Negative 1 minus negative 1, oh, that's 0. 11 minus negative 1, that's positive 12. And 35 minus 11 is 24. Second differences are not constant, so it's non-quadratic. So no first, no second degree. And we're moving on now to our last hope, the third differences. So we have 0 minus negative 12, positive 12. 12 minus 0, 12. 24 minus 12, oh, that's 12 again. So third differences are constant, which tells us that this is a third degree polynomial. So this must be a cubic function. So we're going to say that in all third degree polynomial functions, the third differences are constant. But how can we explore the relationship between the differences and the coefficients in a cubic function? So for this, we are going to do something similar that we did with quadratics. So we are substituting the values of x into the polynomial of the form ax cubed plus bx squared plus cx plus d. I did this in advance, and this is what we got. When x equals -2, then we have a times -2 squared. So I'm going to do this, just the first one, to show you the way. So a times -2 to the power of 3 plus b -2 squared plus c times -2 plus d. Now, -2 to the power 3 is -8, so -8a will be the first term. -2 squared is 4 times b plus 4b, and then minus 2c, and then plus d. And in the same way, we find all the y values. Now we do the first differences, and I'm going to show you as an example the differences between the first two y values, so y value minus the previous. And I'm going to show you how I did it only in one of the differences. It's the same for the rest of them. So we have -a plus b minus c plus d. Take away -8a plus 4b minus 2c plus d. So we have this, and we are subtracting the previous y value, which is right here. So when you simplify, we have in here -a minus -8a, which gives positive 7a, positive b minus 4b, which gives negative 3b, negative c minus negative 2c, which gives positive c, and d minus d will give 0. So that's where we got the first differences from. And you continue in the same fashion for the rest of them. As you see, first differences are not constant because it's a cubic polynomial function. We continue with the second differences. Again, we find them in the exact same way. So we subtract a minus b plus c minus 7a, 7a minus 3b plus c. And the second differences will be -6a plus 2b, and then 2b and 6a plus 2b and 12a plus 2b. Obviously, the second differences again are not constant, so continue with the third differences, and we find that the third differences in this case would be 6a. So let's draw some conclusions here together. So in a polynomial function ax cubed plus bx squared plus cx plus d, the third differences are constant, and they equal 6a. When you think about a is a leading coefficient, right? So that means that if you want to find the value of a from the table of values, then we have to look into the third differences, which represent 6 times the value of a. So in other words, we'll be able to find a as 1/6 of delta 3. Another important coefficient we can easily obtain from the table is the coefficient d, which will happen at x equals 0. So the coefficient d would be equal to the y value at x equals 0. Now, we're going to use these two pieces of information to find the equation of a cubic polynomial function. So here is our first example. So we are given a polynomial function by a table of values. We don't know its equation, but we'll find out what it is. I first always check with the x values. They must differ by exactly 1 unit for me to be able to draw the conclusion or to use the information that we just deduced from our observations. So starting with delta 1, -13 minus -48 would be 35. -2 minus -13 will be +11. -3 minus -2 would be negative 1. Negative 4 minus negative 3 would be negative 1. And 7 minus negative 4 is 11. So obviously it's nonlinear because the first differences are not the same. Moving on to second differences, we have 11 minus 35 is negative 24. Negative 1 minus 11, that's negative 12. Negative 1 minus negative 1, 0. And 11 minus negative 1, positive 12. So we're going to say one more time, non-quadratic, because second differences are not the same. So last but not least, let's check the third differences. Negative 12 minus negative 24, that's 12. 0 minus negative 12 is 12. And 12 minus 0 is also 12. So voila, we have a winner here. So this would be a cubic function because the third differences are constant. So remember that we are trying to find the equation of this cubic function. So we are trying to find something in the form y equals ax cubed plus bx squared plus cx plus d. And there are two coefficients that we can get from the table of values and from the differences. Remember that the coefficient a, as we mentioned, would be 1/6 of delta 3. So we'll say that a equals 1/6 of delta 3, or 1/6 times 12, which equals 2. So we got our first coefficient, and we also know what the coefficient d is, because d would be the y value at x equals 0. When you look at the table of values here, the y value at x equals 0 is negative 2. Which means that the value of d must be negative 2. So we have two coefficients in hand now, and we are going to substitute them into the equation y equals ax cubed, so 2x cubed, plus bx squared, plus cx, and then d is negative 2, so minus 2 at the end. So we will be looking for two coefficients, b and c. When we are looking for two unknowns in an equation, we have to build two equations. So we can use any set of, or any two sets of ordered pairs from the table. I usually prefer to use sets that are represented by smaller numbers. So I'm going to pick 1, negative 3, and maybe 3, 7. They're positive. So I would say that 1 and negative 3, I'm going to add a page in here, is a set of ordered pairs that should satisfy the equation. I'm going to make it green. And also 3 and 7 is another ordered pair that satisfies the equation. So which means that if I substituted the x and the y values into the equation, then we'll still obtain the same equation. So here we go. So we have y, which in our case now is negative 3, equals 2 times x would be 1 to the power of 3 here, plus b times, sorry, 1 to the power of 2, and then plus c times 1, and then minus 2. So in a more simplified form, we'll have negative 3 equals 2 plus b plus c minus 2. Let's simplify it some more. So b plus c would equal the 2 and the negative 2 simplify, negative 3. This is the most simplified form of this equation. We're going to leave it here for the moment. And now we are going to obtain another equation by substituting x by 3 and y by 7. So we have 7 equals the value of a is 2. X this time would be 3. And then plus the b value multiplied by x to the power of 2, so that's 3 squared, plus the c value multiplied by x, which is 3, and then minus 2. Let's simplify. So we have 7 equals 3 to the power 3 is 27 times 2, 54, plus 9b plus 3c minus 2. So simplify some more, and we'll have 7. 54 minus 2 is 52 positive. Take it to the other side. 7 minus 52 equals 9b plus 3c. And 7 minus 52 will be equal to negative 45 equals 9b plus 3c. And they're all divisible by 3, so let's simplify. We want the equation to be in the simplest form because we will have to use this equation with another one. So things get complicated when the equations have larger coefficients. And here is our second equation. So what we're going to do is we're going to bring equations 1 and 2 together in order to find the values of b and c. So I'll start by writing the first equation, negative 3 equals b plus c, and negative 15 equals 3b plus c. Obviously, you can use any method of your choice. Substitution and elimination are both very popular ones. I prefer elimination, and what I'm going to do is subtract the second equation from the first. So negative 3 minus negative 15 would be positive 12. b minus 3b is negative 2b, and c minus c equals 0. That will give b equal to negative 6. And to find c, I will use equation negative 3 equals b plus c. Now that I know b, I can substitute by negative 6. And it seems that c equals 3. So by now we found all the coefficients. So coefficient A was 2, coefficient B is negative 6, C is 3, and D was negative 2. Therefore, the equation of this polynomial function will be y equals positive 2x to the power of 3 minus 6x squared plus 3x minus 2. And there is another example that you can try on your own if you wish, just for practice. And this is the lesson on finite differences in terms of families of polynomial functions. So I hope everything made sense. And let me know in the comments if you have any suggestions or anything else that you would like me to talk about in the future lessons. Bye for now, and thank you for learning from me.